Hello my dear friends, welcome to my YouTube channel. Myself, Dattu Patel, Assistant Professor from SJIT. In this particular unit, System of Linear Equation and Matrices, we are already discussed about the row echelon form, reduced row echelon form, rank of matrices, system of non-homogeneous linear equations, system of homogeneous linear equations, or a Gauss elimination method, Gauss Jordan method, etc. Today's session we are going to discuss about the inverse of a matrices. You all are already learned in 11th-12th science inverse of a matrices by the determinant method. That means A inverse equal to adjoint of A upon determinant of A or a mod A. In this semester, we are finding the inverse of matrices with the help of Gauss-Jordan method. Here, basically, matrix is a non-singular matrices and singular matrices. That means, if determinant of A not equal to 0, then it is non-singular matrices. If determinant of A equal to 0, that means it is singular matrices. Let's start with inverse of matrices. Let capital A be any non-singular matrices. If it is non-singular matrices, then determinant of matrices, that is non-zero, means not equal to 0. Then we can written as capital A equal to IA. Here I indicate by the identity matrices. If we applying the suitable elementary row operation or a row transformation of the matrices A on the LHS portion and to the identity matrix on the RHS portion simultaneously. Means whatever the operation we apply in LHS portion, that is automatically apply for the RHS portion in identity matrix. Then our matrix A is reduced to the identity matrix and identity matrix is reduced to the matrix B, where I equal to BA, where B equal to A inverse. Here our matrix A making the identity matrix, and whatever the operation which is applied in this form, then identity matrix becomes the matrix B, which is another matrix, that is our A inverse. That is exactly we have to find, or our matrix A making the identity matrix with the help of row operation. Let's see one example. Find the inverse of the following matrices by the Gauss-Jordan method: 266, 276 and 277. Firstly, whatever the matrices which is given, that is our capital A, 266, 276, 277. Firstly, A inverses exist or not. For that, we have to find the determinant. If determinant not equal to 0, then A inverse exists. If determinant equal to 0, then A inverse does not exist. That means if matrix is non-singular matrices, then A inverse exists. If it is singular matrices, then A inverse does not exist. For that, we have to find the determinant. Here, determinant of A equal to 266, 276, 277, or that is 2, which is not equal to 0. Here, determinant not equal to 0, then we can say that A inverse exists. Now, applying the Gauss-Jordan method, then we have A equal to I into A. Here, our question which is in form of 3 cross 3 row, 3 cross 3 matrices, means we have used identity matrix of the 3 cross 3. Then we can write A equal to I3 into A. Then here 266, 276, 277 equal to 100, 010, 001 into A. Here whatever the row operation which is applied in RHS portion, that is automatically applicable for the RHS portion. Now our matrix capital A to making the identity matrix, then for that apply the row operation, and whatever the row operation which is applied in capital A, which is automatically applicable to the identity matrix. And for reducing to the reduced row echelon form, at last our matrix A becomes identity matrix, and for that position our identity matrix becomes the unknown matrices, that is B, or that is the matrix B equal to A inverse, that is our exactly inverse of the matrices. For that, making the leading element 1, and for that divide by 2 to the first row. Then we can write 1 half into R1. Then our matrices become 1 3 3, 2 7 6, 2 7 7 equal to 1 half 0 0, 0 1 0, 0 0 1 into A. Now our leading element 1, and making the below's entry of the leading to the 0. For that, applying the row operation, which is R2 minus 2R1 and R3 minus 2R1, and that will give you 1 3 3, 0 1 0, 0 1 1 equal to 1 half 0 0 minus 1 half 1 0 minus 1 0 1 into A. Now with the help of second row has a leading 1, and with the help of that leading, making the bottom entries of leading to the 0. For that, applying the row operation, which is R3 minus R2, that will give you 1 3 3, 0 1 0, 0 0 1 equal to 1 half 0 0 minus 1 1 0, 0 minus 1 1 into A. Now we have the in diagonal elements are 1, and bottom elements of the leading one, that is 0. Now with the help of last leading, making the above entries of the leading one, that is 0. This matrices, that is our row echelon form. Now for the making the reduced row echelon form, applying in last column, that is R3 R1 minus 3R3, that will give you 1 3 0, 0 1 0, 0 0 1 equal to 1 half 3 minus 3 minus 1 1 0, 0 minus 1 1 into A. Now in second column has a leading 1, with the help of above entries of the leading to making 0. For that, R1 minus 3 R2, that will give you 1 0 0, 0 1 0, 0 0 1 equal to 7 by 2 0 minus 3 minus 1 1 0, 0 minus 1 1 into A, which is A kept as it is for the all these operation. Now this is our exactly reduced row echelon form. Then our matrices becomes identity matrices, and whatever the matrix in identity matrix, that becomes matrix B. Then here capital B equal to 7 by 2 0 minus 3 minus 1 1 0, 0 minus 1 1, that is our exactly B equal to A inverse. That means our matrices becomes I3 equal to A inverse into A. Hence A inverse equal to 7 by 2 0 minus 3 minus 1 1 0, 0 minus 1 1. That is exactly we have to find. Let's see one more example. Find the inverse of the matrix by the Gauss-Jordan method. 1 2 3, 2 5 3, 1 0 8. Here we can also use the 3 cross 3 matrices. Suppose you can also solve the 4 cross 4, 5 cross 5, and so any number of rows, any number of columns. For that you can find the inverse of the matrices. First, let the capital A equal to 1 2 3, 2 5 3, 1 0 8. Firstly, we have to check the determinant equal to 0 or determinant not equal to 0. If determinant not equal to 0, then A inverse is exists, means that is non-singular matrices. Here determinant of A equal to 1 2 3, 2 5 3, 1 0 8 equal to 1 into 40 minus 2 into 13 plus 3 into minus 5, that is minus 1, which is not equal to 0. Here determinant not equal to 0, then A inverse exists. Then applying the Gauss-Jordan method, then we have A equal to I3 into A. Here our matrices becomes 1 2 3, 2 5 3, 1 0 8 equal to 1 0 0, 0 1 0, 0 0 1 into A. Now for the applying the row operation, for that making the leading element 1. Here in first row, first non-zero element, that is our leading, that is 1. Then for that making the entries below the leading to the 0. For that applying the row operation, which is R2 minus 2R1 and R3 minus R1, that will give you 1 2 3, 0 1 minus 3, 0 minus 2 5 is equal to 1 0 0 minus 2 1 0 minus 1 0 1 into A. Now first column has a leading 1, bottom entries, that is 0. Now in second row, first non-zero element, that is 1. Then with the help of that leading element, making the below and above entries to the 0. It is not necessary First we have to apply the row equivalent form, then after reduce row equivalent form. You can apply the both the operation together as you like. First you want to convert the row equivalent form, then after reduce row equivalent, then you can also solve it. Otherwise you can apply the simultaneously operation for the leading one, making the bottom entries and above entries of the leading one 0. Here we applying the operations for the together of the leading one bottom entries 0 and above entries 2 also making the 0. For that apply the row operation, which is r1 minus 2r2 and r3 plus 2r2, and that will give you 109 0 1 minus 3 0 0 minus 1 is equal to 5 minus 2 0 minus 2 1 0 minus 5 2 1 into a. Now to making the third row has a first non-zero element, that is minus 1. For that making the 1, and for that applying the multiplying with third row as a minus 1, and that will give you 109 0 1 minus 3 0 0 1 is equal to 5 minus 2 0 minus 2 1 0 5 minus 2 minus 1 into a. Now we have the third column has a leading 1, and for with the help of above entries to the making 0. For that apply the row operation, which is r1 minus 9r3 and r2 plus 3r3. Our matrices becomes 1 0 0 0 1 0 0 0 1 is equal to minus 40 16 9 and 13 minus 5 minus 3 5 minus 2 minus 1 into a. That is our exactly reduced row equivalent form, and that is our in form of I3 equal to A inverse into A. Then identity matrices, and whatever the operation which is applying original matrices, and we convert to the identity matrix, and at that situation our identity matrix becomes the another matrices, that is B, where B equal to E inverse A. That is our exactly A inverse, which is minus 14 16 9 13 minus 5 minus 3 5 minus 2 minus 1. This is all about the practice example, which is do yourself or try it. In this particular example, example number 4 and 5, we have the system of linear equation, and we have to find the inverting the coefficient matrices. Here firstly we have to find the coefficient matrices, means with matrix which is in form of Ax equal to B, and for that whatever the coefficient of x y z, that is our coefficient matrices A, and finding the A inverse of that particular matrices. Suppose we have to finding the values of x y z. For that we have the matrix in form of Ax equal to B, then x equal to A inverse B. Then whatever the A inverse, which is our inverting of the coefficient matrices, and product of that inverse into B, then we get the values of x y z. Example number 4 and 5, we can solve same method. This is all about the topics of the inverse of the matrices. I hope you guys learn something from this video. If you like this video, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorial like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. If you have any query regarding this topic, then feel free contact me. Thank you so much for watching me.